We are live. Hello, everyone. In the last session, the last but not the least, Adam today, which will be talking about hacking C#. So we have high expectations about hacking it. I believe we will hack it from upside down and so on. So without further ado, because we are really waiting for your session, Adam, you will introduce yourself. So I'm just hiding myself. I'm listening from the back. Have a nice session.
Cool. Thank you, Konrad. Hello, everyone. My name is Adam Furmanek, and I'm glad you're attending this talk, Hacking C# from the Inside. Before we actually begin, a couple words about me. I'm a .NET developer or generally software engineer for a decade now, also a blogger and book writer. There are two books which I released, one about .NET, the other one about maths and integer linear programming. I blog at blog.adamfurmanek.pl. I encourage you to take a look if you are interested in internals of .NET, programming models, Turing machines, anything related to software engineering. You can find it there. If you'd like to drop me some questions, feel free to use my email or Twitter, whatever works for you. Also, there is QR code in this presentation, so you can download slides from my webpage. That would be it. Let's now move on to what we are going to talk about today. So Kevin, which you probably know, is very interested in all those deep internals of .NET platform. And I myself, I'm also interested and very happy that I can present things around hacking C#, .NET, and all that stuff which is happening under the hood. And once Kevin told me that I always show how to do these things, or actually how to use these things, but I never show how all these things work under the hood, how I do those building blocks, which I can then compose to hack C#, hack .NET, hack the platform, and use it from here and there. So this presentation is all about those building blocks, how to hack methods, how to hack fields, how to make multiple inheritance in C#, all that stuff, which is not necessarily useful per se in isolation, but it's very useful to actually do or achieve other things around the platform. And we'll see a couple business or practical use cases of hacking things around, but mostly during this presentation, we are going to learn how to build these things. So we are going to learn how to hijack methods, or how to override machine code of some methods, or how to do multiple inheritance, or how to abuse type system, etc., etc. All those things which you can later use to build up some bigger demos. So the agenda for this talk is, first, we are going to go through multiple examples. Some of them are level 200, some of them are level 400. They are generally not related to one another. So if you get lost, or if you feel lazy and don't listen to what I'm showing to you, that's perfectly fine. You can later catch up with some other examples. That's perfectly fine, because they are mostly not related to each other. We'll start with some, let's say, high-level C#. We'll start with avoiding dynamic dispatch. We'll see how polymorphism works in .NET platform, and then we'll start going down. So we'll await async void methods in C#. Then we'll start running some machine code from byte arrays. We'll catch Stack Overflow exception, catch unhandled exceptions, and all that stuff. And finally, we'll land with abusing type system to either serialize something which is not serializable in .NET, or to implement multiple inheritance. So let's start with avoiding dynamic dispatch. So let's say that what we have here is we do have this class hierarchy, as you can see on the left side of the screen. So we have three classes: base, derived, and derived 2, right? And there is virtual method void foo, which accepts one parameter, prints it, etc. So what we would like to do is we would like to create this instance of new derived 2. So we would like to create instance of this class and assign it to the type of the base class. And as you probably know, polymorphism here works in this way, that when we call b.foo, even though that b is actually perceived as of type base because we have dynamic dispatch, because we have late binding, this foo will be actually executed from derived 2, because that's the true type of b variable. The question is, can we actually change it? Can we control that? Is there any way for us, for instance, to call method from derived in this place instead of base nor derived 2? And the answer, in order to answer that, we need to understand how our methods code in .NET. And there are actually two instructions on intermediate language level. First of them is called call. The call instruction is used to call methods which we indicate or which we provide by the method descriptor. Method descriptor in .NET platform is like a tiny piece of metadata or a tag around the method which holds some pieces of information like method name, method parameters, etc. Method descriptor is actually something which is being used by reflection mechanism in order to investigate the method. So we can see, we can ask what parameters does this method accept, and this is all extracted via the method descriptor by reflection. And to call the method with call instruction, we need to provide this method descriptor, and it's like early bound, meaning that we provide this method descriptor and it's being called directly. This call instruction is used, for instance, to call static methods, is used to call constructors, can be used to call any other method. But when we do call methods which are supposed to be polymorphic, we use different instruction. And the compiler emits instruction which is called call virt, like call virtual. And this instruction does the late bound method resolution. So it takes the true nature of the object, the true type, and investigates which method should be called. So in our typical example from the previous slide, it would call the method foo from derived2 class, because thanks to the virtual dispatch. So the call is based on what we provide in the source code, and call virt is based on what we provide in actual runtime. Now the question is, can we use that in order to avoid dynamic dispatch? And the answer is yes. We can generate some code which is not yet a machine code, it's just a regular intermediate language code. So what we are doing is we are creating the instance of derived2, and we would like to call method foo with some parameter which is like calculated, so it's not hard-coded, nothing like this. So we would like to emulate that this is a true nature, like a true running application. And we would like to call it invoke the method which is in the derived class. We are actually using here a Lambda expression. So this Lambda does not get evaluated at any point automatically. It only describes what we would like to call, right? So this 123 plus 456 is not evaluated in compile time. It's actually compiled to the expression tree, so we can see what we are doing. So in order to call this method, call this foo from derived class, what we do is first we get this caller, so we get this lambda, and we check whether it's of type expression call. If it's not, then we throw that, hey, that's not what we are expecting. Then we actually cast this lambda to proper type, and then we get all these arguments, right? And then comes the actual, not that magical magic in this example, but we get the type of t, where t is actually provided as a generic argument, right? So we get the method by name, matching the parameters which we provide, and then we actually get some code which will call this method. So what we need to do is, when we scroll up to the original code, we can see that we are performing some calculation here, right? 123 plus 456. So we need to evaluate this argument manually. So what we do is we start emitting some intermediate language code. We start with a IL instruction to load arguments on the execution stack. Then we iterate through all the arguments and we evaluate them if needed, okay? The only thing which is actually important here is that if we are dealing with value type, they may be boxed because of how these things work under the hood. So we evaluate this argument, and then ultimately we emit the instruction call here, the one we mentioned in the slide, which will perform the early bound, the static bound. So it will run the method from the class derived, right? So it's not derived to nor base, it's derived as expected. So this is the way of how we can actually avoid dynamic dispatch in C#, and how we can generate some code to call any method we would like to, we wish. Now, we are going to stay on this high level of C# language, no machine code, no hacking yet. What we are trying to do now is we would like to await async void methods. And this seems to be contradictory, right? How can we await something which is void, which does not return us anything awaitable, not a single awaitable type, which we could use to actually await for it? So the thing is, we cannot do it directly. because, well, the method returns void, returns nothing. But what we can do instead, we can re-implement a couple things under the hood, namely synchronization context, task scheduler, and thread pool, in order to get our hands on the thing which is under the hood. And this thing is basically a task. Once we get this task, we can await any async void method. So let's do this. So we will now try running this catch async void thingy. So let me just set it as a startup project, and we'll examine the code, how it works, okay? So what we are doing is, if we scroll to the very bottom of this application, of the source code, is we do have this async void method called throw, which throws basically, which waits for a second and then throws some exception. If you do understand how async and await work in together, you probably know that, hey, this exception is going to crash your application because it's propagated in the so-called out-of-band manner. If you would like to learn more about these things, that I have this talk called Internals of Async in .NET, so I recommend you take a look if you are interested how all these things are implemented. But generally, this is the method we would like to call. Now, how do we get the task which is inside this method? Because it must be somewhere over there. So the first thing we do is we implement our custom task scheduler. So task scheduler, which is a piece of machinery used to schedule tasks in the .NET platform to be executed one by one. We have a very trivial, very naive implementation of task scheduler. So we just create a blocking collection of tasks. And then in task scheduler, whenever we want to queue the task, we just add it to this blocking collection. And then we can try executing this task, which is basically an override or calling a base method from this task scheduler. So there's nothing fancy in here. The next thing we are going to do is we are going to create a custom synchronization context. In this context, we create our custom task scheduler, and we are also creating a task factory, which is hiding the original task scheduler, meaning the default task scheduler provided by the .NET platform. But instead, we use our custom task scheduler. What we do next is, whenever we want to post some task on this synchronization context, we basically use our task factory to create the task, and we use our scheduler to schedule it. We can also perform some simple calculation, how many operations are flying currently, how many of them are running. And then we provide a very simple helper method, which we call run, which takes the current synchronization context of the task, replaces it with our custom one, and then in our custom synchronization context, what it does is it goes through the context and through the task scheduler, extracts all the tasks which are supposed to be executed, and then executes them one by one. So that's the idea. Whenever there is a continuation created under the hood because we call some task, this continuation is going to be executed on the synchronization context, which is currently set up, which is our custom synchronization context. So this continuation will go through our context, through our task factory to task scheduler, and ultimately will land in this collection again. We can get this task later on with for each as long as there are any other tasks to execute. And finally, what we do is we restore the original synchronization context. So what we do next is, instead of calling this method throw, which as we remember is just async void method, instead of calling it directly, we ask our context to run this method, and we provide a lambda which will execute it. And now this method myContext.run, it returns a task. And this task we can actually use to just wait for the method. So we can either call task.awaiter.getResult, we can call task.wait, we can await this task, we can do whatever we wish in order to wait for the execution. We then sleep for a second and print that we are done. And as you can see here, the exception was being thrown, but we are done and it does succeed. So this application works properly, even though the exception was thrown somewhere inside the async void method. We can first await the method, and second, we can actually catch all the exceptions which are under the hood. So that would be it when it comes to awaiting async void methods. Now we can move to something a little hacky now. So we would like to run machine code from a byte array. So in order to understand what we are trying to do, first, we need to learn how functions are implemented in .NET Platform. So whenever you do write some function in C# code, this C# code is first compiled to the intermediate language part, which is done by the C# compiler, right? But then this intermediate language needs to be ultimately compiled to the machine code of the platform you're running on. This is generally typically done by the so-called just-in-time compiler. So the method is JIT compiled. So it is compiled only when it's needed. So whenever we do start the application, most of our methods are not yet compiled to machine code. Only when we start calling these methods, they do get compiled by the JIT compiler. The thing is, we can do this in advance by in the so-called ahead of time compilation manner, and the tools for that are called Engine in .NET Framework or ready to run in .NET Core later on. So generally, a function needs to be compiled most of the times twice. First from C# to intermediate language, and then from intermediate language to the machine code. But it's not the end of the world. Starting from .NET Core 2.1, as far as I remember, a single method may have actually multiple machine codes because we have so-called tiered compilation. So the first compiled machine code is the dumbest one, just doing the job, and then .NET tries to get some metrics to profile the method, and then performs the profile-based optimization of the method and compiles it again. I may be wrong here, but .NET 6 tried to disable this by default. In .NET 5, it was enabled by default, so your mileage may vary, but generally .NET does support this multi-tiered compilation. Now, the thing is, whenever we are talking about methods in C#, what we do not think about is how these methods are called. And this is so-called calling convention, which dictates how we pass parameters, how we pass the this pointer to the instance of the object, how we return the value from the function, whether it's like integer, whether it's float value, whatever else, whether it's passed through EAX register or something else. All these details are specified by the so-called calling convention. And this calling convention gets very important once we start generating the machine code manually. Because what we would like to do now is, instead of writing C# code, and instead of writing intermediate language code as we did in first demo, what we are going to do now is we will write a machine code directly, not even an assembly code. Assembly level is one level above because it's slightly trickier, or it's slightly more magical, because one instruction in assembly language can be actually compiled to different instructions in the machine code, like different numbers. So what we are trying to do now is we are generating a machine code. And the thing about machine code is we need to adhere to all the things around calling convention, meaning how we pass parameters, how we pass this, how we return value, what's the endianness, how our instructions encoded, everything else. And bear in mind that what we are doing here is I'm running these examples on x64 architecture, and they do work here no matter what the operating system is. You can do this in Windows and Linux, wherever you wish, because it's the architecture what dictates how you write this code. It will obviously be different if you try to run these things on ARM architecture or some other architectures, but general idea will always be the same. You write some architecture specific code, and then you tried executing it. So how do we do that? The first thing, typically when we would like to write some machine code, is, well, do not write machine code directly by hand. Start with assembly language, so you can go to link or many other pages which are there on the internet, write some assembly code and get the machine code. And you can actually see that the machine code for what we are doing here is written here. So this move EAX 123 in actual machine code is represented as this series of bytes. So we would like to put these bytes in the byte array and start executing that. And how can we do that? Well, there are actually two ways of getting your hands on the actual machine code to execute. First is called getDelegate for function pointer. It's a method provided in Marshall class, which allows you to get an actual pointer to the machine code, which you can use later on to pass either to native code, or you can call it directly, as we'll see in a second. And the other trick we can do is we can modify some other existing machine code and jump around our virtual memory space to jump to the code we would like to execute. So what we are going to do is we'll see both of these methods implemented. So we'll start with the method of marshalling, so getDelegate for function pointer. So the project here is called byte to func marshal. Let's first set it as start a project. Let's run it, compile it, and see what is going on here. So what we are trying to do is we'll skip first through some not relevant code is, first thing is we would like to provide a two delegates. So we'll call two different methods just to show two different examples. First method is basically an action of type int. I'm not using the generic action thingy due to reasons we'll see in a sec, but this is basically an action of type integer. So a method returning void, accepting one int parameter. The other type is function of type int to int. So we accept integer parameter and return this integer parameter. What we would like to do now is, let's say that we start with func test example. We generate some machine code, which is basically adding 4 to the parameter we pass through the stack. So what we are dealing with is we generate machine code which first gets the parameter from the execution stack, which is in register ESP plus 4 bytes, because the first 4 bytes are occupied by this instance. So we get the first parameter, move it to EAX registry, then add 4 to the register, and we finally return this value. So we get this function delegate to this machine code, and we try executing it with value 23. So it should give us 27. And as you can see, if we check the output, you can see 27 is right here. So it did work. Now the question is, how does it work? So if we go to this generate thingy, we need to do a couple things. First, we get this byte array of our machine code. The first thing we would like to do is, and bear in mind, I'm running this directly for 32-bit architecture. Even though I'm running this on 64-bit processor, doesn't matter because we still can execute 32-bit applications. So I'm just dealing with integers, not with longs, but you can obviously make it generic to use int pointers, etc., etc. But to keep it simple, I'm assuming integers anywhere, and we are 32-bit architecture here. So we do get the array code address. So we get the address of this array, and we also pin it at the same time. So garbage collector does not move it anywhere. And then we get the first byte in this array, which is first byte of our machine code. And if you know how structures are implemented in .NET, I mean how this data structure is implemented in .NET, is the first 4 bytes, they do indicate the length of the array. There is a type of the array, and there is the length of the array in this byte array, right? So the type tells you that, hey, this is an array of bytes. So reflection does work, and .NET can verify types. And the other, the second integer over there is the size of the array, how many bytes we store over there. So we need to skip those two integers. So we move our pointer by 8. We finally get the address of the machine code. We unlock this page so we can start executing the code. So we ask the operating system, hey, take this page of memory and make it executable. Okay, and for that we just call win API. Finally, what we do is we call get delegate for function pointer of type T. So we get our delegate basically to this machine code. We cast it twice to get the proper type checks, and that's it. So this is how it works for funcs. Now, the same thing is going to happen for actions. But for action, we are going to do something actually different. Because for action, what we would like to do just to show that, hey, we can do all this stuff, is we not only execute the code, but we also jump somewhere else. So in this action int, what we would like to do is we would like to start executing this machine code and jump to some other method. And this some other method is basically my write line. So I will execute this machine code, which effectively jumps to this .NET method. And in order to adhere to the calling convention, I need to have two dump parameters just to adhere to how parameters are passed through stacks and register. And I get this integer, which I am printing out. So notice that even though I execute the machine code from here, I can still technically do some sort of calling of of .NET functions. And you can see that, hey, I'm in write line and it does work. We do print out parameter 5, which we passed over there. So this is how we do it with generate get delegate for function pointer. The other trick we can do is actually we can do the same, but with jumps, with modifying machine code directly in place. So what we can do is we start with similar setup to previous demo. So we will have two examples, one for actions, one for functions. Now what we do is we define a base class which will hold one integer field which will hold the address of the actual method we would like to execute. Now we derive from this base type with two different delegate-like types, so the action int and the func int, and both of them implement a method called stub which accepts parameter and has some machine code. And this machine code is going to be irrelevant for us because what we are going to do is we'll get an instance of this action int, override this machine code generated from console write line, and jump from here to the address specified in this target field held by base type. So what we are doing again with func is we do have some machine code which does the same, adds 4 to the integer, but in generate what we are now doing is we first spin the array again, we get the address of the machine code, we unlock the page again, and now what we are doing is we get the array code address and we store it in this type which derives from this base. Okay, then we get the delegate for the method called stub, and we prepare this method so it gets JIT compiled properly, and finally we modify the code, the machine code of this method called stub, and we insert the code which basically what it does is it pushes the parameter to the stack and then returns, so it effectively jumps to some other method. So what is now happening, apart from that the code works, there is one very interesting thingy about how it works. Once again, we take the action example, but this time we are calling getType and we are printing where are we. So notice that when we execute this method, we are in myWriteLine, and even though the method myWriteLine was declared in class program, .NET Platform thinks that the actual type is called byte to func.actionInt. How is that possible, and why is that? That is because whenever we get this action int and we get the stub method, we modify the machine code from here to jump to myWriteLine. So even though .NET thinks that we are still executing this method, we are actually running code from some completely different place, and .NET does not track that. So this is another example of how we can hijack method, how we can execute any code from machine code. Now what we are going to do is we are going to actually start hijacking methods. So we will learn how to make one method execute something completely different. So what we are going to do is we would like to modify metadata or modify the code under the hood to see that we can effectively make .NET execute different methods than it's supposed to do. So in our test class, we will have multiple methods like return string and return string hijack. So you can see return string just returns original string, return string hijacked returns modified string. So what we would like to do now is we would like to create an instance of test class and modify it in a way that whenever we call return string on instance of test class, actually return string hijacked is being executed. So we are trying to do this some sort of method override on static methods, non-virtual methods, whatever we wish. How are we going to do that? So first we call return string like the regular way, and we can see that in output it does print the original string, so nothing changes yet. And then we hijack this method. So instead of calling return string, a return string hijacked is being called by .NET Platform. And we call return string again, and you can see that the second time modified string is being returned. How is this possible? So what we do in hijack method is we are getting those two methods, the original string, return string, and the return string hijacked. We compile these methods with JIT compiler, so we do get machine code generated. And then we get pointers to machine codes of these two methods. And actually .NET allows us to do that, so gives us the code, gives us the pointers to these machine machine codes. Bear in mind, get function pointer may not be super reliable if you have multi-tiered compilation environment, or depending on what methods you're actually dealing with, because depending if those methods are like engen, they are pre-compiled, compiled in ahead of time mode, this function pointer may not work reliably. But generally, there are other methods to get pointers to the functions, but in this demo, we're just using the simplest one. So we get the addresses of these two methods, we unlock the pages, and what we do next is we modify the original method and we insert a jump instruction. So we actually, again, start executing the original method, and then the very first instruction of this method is jump to the other method. So we jump from one method to another, and in that, once we land in this target method, we just return what's over there. So effectively how it works is we do modify this line of code, like on a machine level, and instead of doing return original string, it does something like jump to return string hijacked. So we jump to this instruction, and then we return modified string. So this is how it works, and you can see it does modify those values, and this is all done on the jump level based on jumps on the machine code. But there is actually yet another method which we can use, which does not use any jumping logic, but what it does instead is it modifies metadata under the hood. So what we are going to do is this time we are doing exactly the same, only we have different way of hijacking methods. So what we do now is we get the pointer to the source method and to the target. We again compile them, etc. But the thing we now do is we get the method descriptor of the original method, and we modify this method descriptor to point to different method. So this time, whenever, and the method descriptor holds its function pointer 8 bytes from the beginning, and we override this pointer to point to direct method. So this time, whenever we call this method return string, it's not that we enter this method, this line of code, and jump to this line of code. It's actually differently. We try calling this method, and .NET looks for machine code of this method and thinks that the code is in this location. So it jumps exactly to different place to our return string hijacked. And you can see that it does work as expected. So this is the other way of how we can hijack methods, how we can jump from one place to the other. And now the question is, okay, those things are really hacky. Are they useful at all? Is there any legit use case? What can we do about that? And the answer is yes, there is. The couple examples unused in production are related to for instance, running things on multiple desktops. So if you do use Windows, starting probably Windows 95 at least, and even older, I guess, there is a thing which is called desktop in Windows, and you can have multiple desktops. Obviously, now in Windows 10, starting Windows 10, there is this nice button which allows you to create multiple workspaces. This is very similar mechanism. We can have multiple desktops. We can move windows between them and organize them to suit our needs. But the thing is, the logic and the machinery for handling multiple desktops was in Windows since very old time. It worked a little differently, but still was exposed by the application, which is called desktops from sysinternals. So we can see here in my the bottom right corner, I do have this application, and I do have two different desktop created. So I can switch between them just by using this application. Now the thing is, we would like to run a method, or sorry, start an application from C#, and we would like to control in which desktop it is being created, in which desktop it is being executed. The thing is, if we try running this process the regular way, meaning we do create instance of process start info, etc., there is no way for us to provide a desktop name using the .NET API, because the desktop name is always zeroed out, so the application starts at the same desktop. How can we do that? How can we override this thingy? Well, the thing about that, how we can fix this, is we can actually override some machine code under the hood. So if we do open the MSDN, and if we see how these things are initialized under the hood, you can see that the startup infrastructure has this LP desktop field, which is initialized and always zeroed out. So this is the field we would like to modify to actually provide the desktop name. Now, how can we do that? Because this startup info thingy is created internally once we call the process start method. So what is happening here is that when we do run process and when we call process start, under the hood, this method creates the instance of this start info structure and initializes all the things. What can we do? In order to provide them the desktop name, we can use multiple tricks. We can, for instance, copy the code from .NET library, maintain it on our own, and replace the desktop name as we wish. It works, but the problem is that it's not supported, meaning that once they change something on their side in .NET libraries, we need to keep that synchronized with our changes, so we need to basically sync the code all the times, which is nasty. The other way is we can drop .NET API altogether and start using WinAPI directly. But hey, we would like to use .NET API because we would like to have these nice process instances, etc., etc. Is there any other way to actually provide this desktop name? There is, by hijacking. So what we are doing is we would like to hijack desktop logic. So what we do is we use reflection to get the all the assemblies and then find the type, which is basically a startup info. So we want to get this type by reflection. Then we would like to get the original constructor of this type and modify it. So instead of calling the original constructor, our custom constructor is being called. And in our custom constructor, what we are going to do is we first initialize the code size field, because that's what WinAPI expects us to do. And then we use reflection to modify this LP desktop thingy. So what we do is whenever we start calling this process.start method, under the hood, this API creates this startup info structure and initializes it by calling its constructor. But instead of calling its normal regular constructor, our custom constructor is being called. So let's see this in action. We can start Notepad.exe and provide custom desktop name. So if I start this application, you can see that the first thing it does create a notepad on this desktop and then waits for console read line. Once I hit enter here, you can see that the application has finished and apparently nothing happened. But once we switch to the other desktop here, you can see that notepad has been started. So this is the way you can hijack methods to actually deliver something usable for your use case. The other thing which we could do is we can, for instance, handle unhandled exceptions on threads. You probably do know that whenever you do start a thread which does not handle all the exceptions, it's going to kill your application. So the thing is, if we try creating a thread which does this, that it prints something and throws the exception, if we run this code like this, it's going to kill our application. And the thing is, we not always have a way to insert try catch inside this Lambda, because, for instance, we are running code from different platform, p-invoking from something, etc. Or maybe we just took Java with IKVM and are executing Java code directly, which maps to these threads and does not handle all the exceptions. What can we do? We can obviously enable handling by hijacking methods again. So we get the original constructor of thread start, and then what we are trying to do is we modify this code of thread start to call our custom thread start constructor, which will get the original thread start and execute it in the try catch block. So once we do it this way, you can see that, hey, exception has been thrown, but it was actually handled and printed out gracefully because we do handle this thread constructor with our custom try-catch block. And we do it completely separately. It's completely external to all the code which uses regular threads, because what we do is we modify the thread constructor like in place by hijacking machine code. The other thing which we can do is we can handle Stack Overflow exceptions in C#. If you know .NET, you probably know that Stack Overflow exception is going to kill your application no matter what. There is no way to gracefully stop it from killing your application. The thing is, why would we ever try to handle Stack Overflow exception? Because, hey, it's a serious bug, right? The thing is, imagine that you are running tests with an unit, X unit, whatever else, and what you would like to do is you would like to run all the tests, and if one of these tests do fail with Stack Overflow exception, you would just like to clean those things up and carry on with other tests. This is not what's going to happen with any unit or X unit or whatever else, because it's going to die and not execute any other of your tests. But if we do modify machine code, what we can do is we can actually handle those exceptions. How do we do that? Instead of calling the method directly, we install the vectored exception handler. So we get the vectored exception handler and add it using Win API. So any exception is going to be routed by our custom logic. And then we use some machine code to actually prepare the stack and remember the stack before calling the method which may cause Stack Overflow exception. So we do save some registers, and only then we call the method which may throw the exception. And once it's called and once it does generate exception, what we do is we have the VEH handler, which extracts the exception code and checks whether it's a Stack Overflow exception. If it is, then what we do is we restore the original registers. So we restore EAX, EBP, ESP, etc., and tell the CPU, hey, it's perfectly safe to carry on, to continue. So CPU basically throws out whole stack which is being invalid and moves to the place, does the so-called set jump, long jump like action to go to the place just before we code the method generating Stack Overflow exception. And then we can just safely carry on. Obviously, no finalizers are called, no finally blocks are executed, but hey, our process still runs. So what we can do now is we can clean things up, restart, or generally save some user data. So these are actual use cases of what we can do with hijacking methods. Now, the question is, what can we do else? We can start abusing type systems. So imagine that each method in .NET must have parameters, must have so-called signature, which specifies names, parameters, return type, etc. And those things are checked by C# compiler when loading the module. But can we in some way abuse this mechanism to actually call some different method on a given type? And the answer is yes. What we can do is we can actually change the type of the instance we are dealing with. So imagine that what we are doing is we do create an instance of class A, and then we call print with A. So we do have method print with A, which accepts instance of class A and calls print on this type. So class A is something which has virtual method called print and does print something and prints the type, okay? Now, we do have completely unrelated class B, completely independent and separate, which obviously by accident has a very similar method. We'll get to this error in a sec, which has obviously a very similar method called print, which is also virtual and which also returns void. So this method prints b.print and then also prints the type. So what we would like to do is we would like to hijack method that instead of calling print with A, we are printing with B. So let's see what happens when by calling print with A, we are actually calling print with B here. And what we have here in this parameter is not the type B anymore, but instance of type A. So we get the instance of type A, and we try calling print method and print2 method on this type, even though the type B is different than what we are getting because we are actually getting type A. So what you can see here is even though we are printing with B, still method print was called from type A, and then we tried abusing type system A by calling print2, which crashed. Why is that? It did crash because we tried to do the polymorphic invocation on type A and tried calling method print2, which does not exist on type A. So we tried calling non-existent method, so it just crashed. But if we remove the virtual specifier from here, what's going to happen now is we are not going to use call virt instruction anymore. We are going to use just the regular call instruction. So instead of calling this with polymorphic invocation, we can see that we called bprint2 on type A. Why is that? Because we are just calling a piece of machine code. So .NET does not verify at this point whether this instance which we pass to this method is actually instance of type B. So we abuse the type system. Can we do something fancy with that? The answer is yes. We can, for instance, start serializing non-serializable things. So imagine that we do have a class which is non-serializable. Okay, so we start with class root, which has non-serializable child, and we just do print. We print our root, and then we call magic on our child, and we just print the child type. Okay, we would like to serialize instance of this type, and this is not going to work because non-serializable child is non-serializable, right? But what we can do instead is we can create a serializable child. So we can create a custom class on the side, which has exactly the same like code structure and the data structure. So the same fields, everything is the same, and with all the methods being the same. And what we can do next is we can create an instance of root with non-serializable child. We can create an instance of serializable child with the same data. And then what we can do is we can get the handle to the root object and modify pointer of the inner field so it points to the serializable child. So once we code this and once we code use a binary formatter to format serialize the serialized things, you can see that it does work because we do change non-serializable child to serializable child. So we modify the instances under the hood, and this way we can serialize non-serializable classes. And the last thing we are going to do is we can implement a multiple inheritance thingy. So obviously in C# in .NET, you cannot do multiple inheritance, but what we are trying to do is we'll morph the instances from one type to the other. So we will have a multiple base interface, which provides us a method to get current state. And current state is basically a dictionary of values which we hold in given instance, and we'll be using that to change the content of the object so it mimics one type and the other. And what we are doing is we have multiple classes like base 1, base 2, base 3, etc. And what's important here is all those classes, they will have exactly the same structure on the field level, meaning that this class has one integer field which is 4 bytes long. This class has one float field which is also 4 bytes long. This class has two short fields which are 4 bytes long, and we do assume they are packed together, so we do not get any alignment or filling between them. So it's again the same data structure, so the same size. And finally, base 4 holds some reference type, which is again a pointer, which is 4 bytes long. So what we can do now is we create an instance of this multiple base. We initialize the state for all the base classes. And what we do next is we can ask .NET to morph the type of this object to actually present the object as instance of a different class. So at this point, our child, which is again the multiple base, is basically going to be considered or being used as base 1. Important thing here is we are not copying this thing to the side. We are not creating a new object on the side and routing to it. No, it's always exactly the same place in the memory, which is only being modified to mimic that it's different type. So here we morph it as base 1, base 2, base 3, etc. We modify all those fields and then come back. And you can see that, hey, we do preserve the instances values even though we change the types of these classes. So while at a given point of time, this multiple base child variable can be of one base class only, we can actually implement this multiple inheritance and morph this instance to be a different type, different instance of different class as needed. So this is what we can do to abuse the type system. And just to sum up, because we are out of time, in order to do all those funny things, in order to generate intermediate language, in order to generate machine code, to hijack methods, to abuse the type system, to call non-existing methods, to serialize non-serializable types, all of the things you need to remember are actually all the deep internals of your platform. You need to understand what your architecture is, what your operating system is, what your memory security is, what platform you're running on, what's the calling convention, etc. You need to understand all these things from very top level down to very bottom CPU bits and bytes, but ultimately it's just a bunch of bytes. And once you get a pointer to any byte in your memory, you can do anything you wish. And that would be it for this talk. This QR code points you to the slide deck, and if there are any questions, I'm happy to take and answer them.
Awesome, Adam. Thank you very much for this mind-blowing talk. Like, we haven't had much questions because probably people were just their head were exploding, so they wouldn't have time for writing. But if we have any more questions, just write it now. Though even we have some. So the very first one is about the slides. So we mentioned this QR code is for the slides. So if you would like, just use it, make a screenshot and use it later on. And the code samples, where are they available anywhere, or it's just the presentation?
They are available on my blog. This QR code points to my blog with slides and all the materials, so you can find them over there. They are scattered through different blog posts inside the .NET internals series on my blog. But yeah, generally they are all available online.
Awesome. There are some comments like about mind-blowingness of this talk. So things how you need to how deep you need to go to make all this happen. One funny comment that you have inspired some PRs in the next days. So good luck.
The thing is, while I do use this code in production and it does work, generally be careful when doing that, especially if you do support multiple platforms, because you really need to understand all the bits and bytes, and they do get tricky under the hood.
Yep. And this is probably the place when comments in code make sense, right? Comments should be self-commenting, but maybe
That's exactly
not that
true.
part. Okay, one technical question. So why do we need to call virtual protect?
That is a very good question. You can see in my source code that I am calling virtual protect in multiple examples, for instance, in method hijacking. The thing is, or maybe not like here as well, because we do call unlock page, what we would like to do is once we generate a piece of machine code, each your page of memory inside your application has multiple permissions. It can be executed, it can be read only, it can be written only, whatever you wish. The thing is, if you have your data and array of bytes in your .NET application is your data, not the code you execute, your CPU and with operating system will not allow you to execute this code because the page of memory holding this array of bytes is not marked as allowed to be executed. So your operating system will show you some nasty segfault exception that, hey, invalid access to memory, whatever. So in order to do that, to execute this code, you need to call a virtual protect from your Win API, from your operating system, or any other method you actually have. Like in Linux, it's some other method, which I do not recall. It's on my blog as well. But you generally need to go and ask operating system, hey, make this page of memory executable. So that's why we call virtual protect. And it's actually important to understand that not all platforms will allow you to do that. For instance, you cannot do that on gaming consoles, and that's why just-in-time compilation does not work over there at all, because it cannot generate the code dynamically. It needs to compile everything in the ahead of time mode. So, but because we are running on x86, we are allowed to call virtual protect, and we can change the page of memory to be executable. That's why we call virtual protect.
Awesome, thank you. We have many thanks about your session and the whole conference. So we are also thanking you in both as Dotnetos and as Adam. One more question is here about the hijacking methods. So can we will we be recompiled ever?
That's a very good question. So we mentioned that there is so-called multi-tiered compilation in .NET now. So it can be recompiled. Method can be compiled many times. The thing is, yes, the method may get compiled again. So your machine code will not be overwritten per se because new machine code will be generated. So yes, the original method will probably never be executed, assuming we did modify the machine code, but some other code may be generated and be executed. If we do override methods using this method descriptor trick, so we go and replace the metadata information, then yes, it may be again compiled and modified to point to some different machine code. I do not think the original code would be called ever, but I'm not entirely sure. I imagine there may be an edge case for doing that, but generally I wouldn't expect this, but different code may be executed anyway.
Awesome. And the next question is about practical usage. You mentioned some, you even showed some scenarios. So your thoughts about that?
Yeah, so the question is whether those bits and bytes are used in production at all. They are. They are. Obviously, most of like 99.9% of applications will never need them. However, those low-level tricks are very often used in to speed things up. You probably know about spans and memory, which became a thing in .NET Core, and they are because all those tricks were used under the hood to some extent to speed things up in your frameworks. So they are not used necessarily on business level code, but generally for like skeletons of the platform, yes, they are used often. And also the examples I provided to you, like running application on different desktop, handling Stack Overflow, hijacking threads, those are all actual use cases of my applications running somewhere in production. So I did commit this code to Git repositories, and it's now maintained and supported and does not crash. So those are actual use cases, although I wish you luck you never have to do things like these.
The question is whether you maintain it or you just left the company and someone has to maintain it.
Well, some of them I do still maintain. Some of them are now long gone legacy code maintained by someone else and hopefully killed by now.
Sure. And I believe the very last question, at least at the moment, can some of your examples be run on Linux?
That's a very good question. Obviously, where applicable, they can. Like the desktop thingy, when you run Notepad on different desktop, obviously cannot because there is no desktop, no Notepad in Linux. However, all the other examples, they can be executed on Linux. Yes, because it's not the question about operating system. It's the question about architecture you are on. If you try running Linux or on ARM architecture, all those examples may require very significant changes or may not work at all because ARM architecture is completely different, right? But generally, all those examples, if you are still running Linux on x86 architecture, then yes, they will work, and they will work exactly the same way because it's about the CPU, not the operating system per se. But sometimes you will need to call some Linux APIs, right, to unblock the memory to make it executable. You obviously need to call your Linux API, not the Win API from Windows.
Yeah. And remember about the different calling convention on Linux.
Yeah, that's obviously again a thingy because in Linux, well, this also applies to whether you're running 32-bit code or 64-bit code. You run different registers, but like to the essence of concept, it is easily portable and should run the same way on different operating system as well.
So no PRs blocked on Linux.
Exactly. You're just a couple more ifs in the code.
Exactly. The question is about hijacking the GC. As far as I remember, you have a session, at least you were hijacking the allocator.
Yeah, that is exactly true. I do have a manual memory management session, which is out there in YouTube. You can find it out. You can take control over garbage collector and allocation mechanisms. You can hide objects from GC. You can allocate them by yourself in the memory area you choose. Again, it's based on some similar concepts unpresented here, and you can do that. But it's a slightly different area than what we presented today, because it's more tied to the GC implementation. So you need to understand garbage collection much more. But yes, the general answer is yes, you can control GC as well. Not to mention that I do believe that, Konrad, you implemented your custom GC, which can be just moved in place and replace the original one in .NET. So that's more civilized version of handling that.
Civilized, a little less harmful hijacking. Like just to add something, Microsoft has added this possibility to plug in your own implementation of the garbage collector, so it can be now replaced by your own library, which will just call your own routines for allocating, and if you want to implement also garbage collector, but for sure you need to implement allocator. So you can do it both ways, like hijacking or just plugging your own library into the runtime.
Mm-hmm.
Okay, the very last question, because we need to slowly finish the thing, so it is probably have been answered, but
yeah. So why did I use these things? I mentioned this throughout this session. For instance, handling threads or unhandled exceptions on threads was because I was using some Java code which was run via IKVM compiler. The thing with Java or in JVM generally is that unhandled exception on a thread does not kill the application in that world, meaning that programmers do not necessarily add global try catch, because it's not going to kill any application here, right? So they are not doing that. They are not adding the global try catch. But because I was just getting this code and porting it to C# like on a binary level, not on a source code level, but on a binary level, well, it was executed using .NET thread, and unhandled exception was killing my whole process. So I was basically forced either to rewrite everything from Java to .NET, or I had to hack it in place. I chose the latter. Similarly with other things, I had to run application on different desktop. .NET did not allow me to do that, so I just hacked it, right? So those are actual use cases where when I was forced to do so, it was not out of curiosity and like just toying with things around. I was more or less forced to do so.
Awesome. Thank you very much for this session, which is just also closing our conference. So thank you very much.
Before we wrap up, just one more slide,
Sure.
couple more slides. If you'd like to learn more about all these things, there are a couple of references here at the very end of this slide deck. Some of them point to books, some of them point to my blog with examples. And being all of that said, it's time for me to call it a day. So I'd like to thank you, and back to you, Konrad.
Thank you. So thank you, Adam. And just stay with me for a moment, because I have the pleasure to close the whole thing. So thank you, Adam. I'm just getting you out of the of the stream, and I'm staying here alone just to give you some thanks, because obviously that is the thing that we need to do at the end, because the whole thing, like the whole conference, cannot happen without sponsors. So we would like to thank again the sponsors that we have, and we have 2 platinum sponsors. So the very first one is Demand, and very, very much thanks for you, Demand. Thank you very much for being as a platinum sponsor, because you have helped us, right? Without you and without other sponsors, we cannot do things like that. So Demand is a pretty big company, and it is here in Poland since 90s. It employs almost 4,000 people, helping to do hearing health stuff. So if you would like to know about them a little bit more, just visit their site and look around what they can offer to you, especially if you are Poland-based, but probably not only. The second platinum sponsor, so another super very big thanks to you, KMD, is another pretty big company, the largest foreign affiliated branch of the KMD group. And they are responsible for important solutions in IT, R&D, support areas. They help Nordic businesses and the public sector to make major leap in the digital evolution. So another super nice company. Very much thank you for being with us, for soaring whole the thing, and also please feel invited to look at their site, because Without such companies, we cannot do nice things. And they are also gold sponsors. The very first one is, let's say, we, because we are Dotnetos, and the gold sponsor is Dotnetos Academy. So if you liked the topics that we have covered, if you like, for example, the multi-threading and async programming and talks about that, or maybe memory or any other performance-related stuff, we really like providing premium content about that. Not only conferences, we were doing meetups, but there is also a bunch of courses, online courses that maybe you will be interested in. So look around at the Dotnetos company site. There is an Async expert course, .NET Memory expert course, and so on. So a lot of very interesting stuff. And also big thanks to JetBrains, because that's another gold sponsor that helped us to make it all happen. And you all probably know JetBrains from their awesome tools like ReSharper, Rider. I personally like the diagnostic tools. So also, if it happens that in any way you haven't heard about them, which may be pretty surprising, but still may happen, just go to their site and see what they are offering for you as a developer. And also, we as Dotnetos really like to be in community, so please use in general Dotnetos hashtag, Dotnetos Twitter handle. Look for us on Facebook if you are using it, and if it happens, it is working. And the Twitter, obviously, we are mostly on the Twitter, so if you would like to ask us for something, ask about our community activities, about our courses, maybe you can suggest something that we can do for you and things that we can learn, teach, simply reach us on Twitter. We are there all the time. Maybe we sleep sometimes, but probably most of the time it will be answered at least the next day, because really like Twitter and tweeting. Or maybe you can go to the .netos.org site, where all our products and other activities are summarized, so you can look simply what we are really doing. So that's all. I'm pretty sad because it is all the conference that I need, unfortunately, to close now. It was pretty nice, awesome, I would say, 3 days, maybe 2.5, because the first day was pretty unfortunate, but still a lot of awesome content. I hope you have learned a lot. I hope that we will meet somewhere, maybe online, maybe on site, but just remember about us. We remembered about you. We are all about .NET community, so I hope we will see you next time somewhere. Have a nice day, wherever you are, whether there is a morning now or maybe evening or middle of the day. Just have a nice day and see you somewhere. Bye.